Okay. Hello, my name is Christy, and this is my Deep Learning with Big Data final project. Hello, everyone. For today's presentation, I have put together this PowerPoint to walk us through the key sections of the project. And so we'll begin with the introduction and project overview, where I will set the stage by explaining the purpose of this project and the data sets that we're using. Next, we'll move into strategy and data pre-processing. Here I'll outline how machine learning is going to be used in the organization and walk us through the steps to clean and prepare the data sets so they're ready for modeling. From there, I'll dive into supervised learning models. I'll show you how I built, trained, and tested models, such as logistic regressions, random forest, and regression approaches for predictions. After that, we'll explore unsupervised learning models, focusing on clustering techniques applied to the CAR evaluation dataset. This section will highlight how unsupervised learning can uncover hidden patterns and groupings in data. We'll then move into model comparison, where I'll evaluate the strengths and weaknesses of different approaches, talk through the performance metrics, and highlight which model provided the most reliable insights. Finally, I'll wrap it up with some conclusions and tie everything together with some key takeaways. Now, let's take a moment to look at the purpose of the final project. At the core, the goal is to apply machine learning concepts across both supervised and unsupervised tasks. In other words, we're not just building models, we're demonstrating the data science workflow from raw data to actionable insights. Now, what data sets are we working with? We've got 4 real-world examples. We have the Austin Animal Shelter, where we predict outcomes for animals. We have the ABA loan data set, where we estimate age based on shelled measurements. We have the adult salary data set, where we classify income levels. And finally, we have the CAR evaluation data set, where we cluster CAR profiles. Together, these cover the full range of model comparison. To make this practical, I'll start with strategy and pre-processing. Part 1, which focuses on how a firm, Astrotech, would adopt machine learning. And part 2, I'll dive into cleaning the Austin Animal Shelter dataset. Then I will move into supervised learning models. Part 3 will be about ABA loan age prediction. Part 4 is adult salary classification. Then we will explore unsupervised learning models using clustering to evaluate CARs. And finally, the last part, we will compare all the models to see which approach performs best. So as you can see, this project isn't just about building models, it's about showing the big picture of machine learning in action across different data sets and problem types. Now, starting off with the publicly listed company, I've been tasked with leading a critical initiative, implementing machine learning across the entire organization. The executive board has made it clear, to stay competitive in our sector, we need to leverage machine learning, not just in isolated projects, but company-wide. so every department can benefit. Now, we are fortunate enough to have the financial resources to execute this strategy at scale. But this way, we will also face aggressive competitors who are already adopting similar technologies. This means our plan needs to be ambitious and practical. So, the strategy that I'm presenting today considers these three pillars. We have business context, technological ecosystem, and human capital. Starting with business context, we will take in consideration the size, sector, and competitive landscape of our company. We will then take a look at the different frameworks, platforms, and systems that we'll deploy, with a focus on scalable data pipelines, cloud infrastructure, and secure integration. Finally, for human capital, we will ensure that our staff has the right skills, training, and readiness to adopt machine learning effectively. Now, by aligning these pillars, we'll create a roadmap that not only introduces machine learning into different workflows, but also ensures it becomes a sustainable advantage. This plan will be detailed, actionable, and ready for execution within our timeline set by the CEO. Moving on to our vision and strategy. Our vision is simple. It's to revolutionize AstroTech into a fully data-driven enterprise that leverages machine learning across all operating systems. Now, this isn't just about adopting new tools. It's about transforming the way we operate, innovate, and compete. To achieve this vision, I've set some clear objectives. First, we'll enhance efficiency through automation and predictive maintenance. Second, we'll elevate the customer experience with personalization, chatbots, and recommendation engines. Third, we'll strengthen risk management by embedding fraud detection and compliance monitoring. And finally, we'll drive innovation by creating new products and leveraging market insights. Our technology strategy provides a foundation. We'll provide frameworks like TensorFlow, PyTorch, Scikit-learn, and AWS. This ecosystem will include a cloud data lake, ETL pipelines, APIs, experimentation platforms, and ML operations. Deployment will be supported by pipelines, model drift detection, dashboards, and most critically, cybersecurity and compliance, while making sure ML is embedded into ERP, CRMs, HR, and customer-facing systems. Now, of course, technology alone isn't enough. Success depends on human capital and organizational readiness. We'll launch training programs, boot camps, and certifications. We'll also assess our current staff's skills, and we'll recruit top talent in AI and machine learning. Change management will be supported by executive sponsorship, a communication plan, and a dedicated machine learning committee. Now, for the implementation roadmap, there is 3 main phases. Phase 1, within the first 6 months, will focus on building data infrastructure and piloting machine learning in marketing and operations. For Phase 2, from 6 to 12 months, we'll scale machine learning into finance, HR, and supply chain forecasting. For Phase 3, over 12 to 24 months, we will fully integrate ML across the organization and establish continuous improvement through machine learning operations. Finally, we'll measure success with KPIs and metrics such as ROI, cost savings, customer satisfaction, and revenue growth. And we'll proactively manage risks, both technical and such as model bias, data quality, and organizational, such as resistance to change or skill gaps, with governance frameworks, ethic boards, and continuous training. This strategy will then ensure that AstroTech not only adopts machine learning, but embeds it deeply into the DNA of the company, creating sustainable competitive advantage. Now, moving on to part 2, Austin Animal Shelter Dataset Cleaning. Let's start with an overview of the dataset. I worked with this dataset, including 95,367 records collected between 2013 and 2020. The attributes included identifiers like animal ID, name, timestamps such as data type, and descriptive fields like animal type, breed, and outcome. From there, I applied several cleaning steps. First, I removed some irrelevant attributes such as ID and redundant date fields that didn't add any value. Next, I converted the age upon outcome field into numeric months. For example, 2 years became 24 months. So the data could be consistent in the modeling. I also handled missing values and some invalid entries such as zeros or blanks. And this way, all the attributes had consistent data types. Now, the result of this process was a structured data set, and I saved this data set as Sheltered Animals Clean CSV. This clean data set is now ready for exploratory data analysis and model training, forming the foundation for the rest of the project. Now, this is an overview of the data pre-processing steps. I turned raw data into a clean data set, starting off with cleaning the data, removing any irrelevant attributes, and the end result was a clean data set. Now let's walk through the key steps of the remaining parts of the project. For this part here, I began with pre-processing the data. And so this included renaming columns for clarity, removing 2 rows with impossible or impossible height values, capping outliers using the IQR method, and also one-hot encoding the categorical feature. These steps made sure that the data set was clean and ready for the next phase modeling. I then moved on to model selection. I chose the logistic regression because the target variable, high ring count, is binary, and logistic regressions are interpretable, efficient, and serve as a strong baseline for classification tasks. For model building and training, I separated the features from the target variable. I split the data into 80-20, my apologies, 80% training, 20% testing, and I successfully trained the logistic regression model. I then tested the model on new hypothetical records. For a mature male, the model predicted a high ring count, while for a young infant, it predicted low ring count. These predictions aligned with expectations. Now, in terms of evaluation, the model achieved nearly 80% accuracy with balanced precision, recall, and F1 score. The confusion matrix showed strong performance, though some false positives and negatives were included. To confirm consistency, I ran a 10-fold cross-validation which yielded a mean accuracy about 77% with low standard deviation. This reinforced the reliability of our results. Finally, in the interpretation of predictions, I can say with confidence that the model provided reliable insights for binary classification tasks. Overall, the workflow demonstrated a solid baseline approach to predicting ABA loan ring counts. Now let's walk through the workflow and results of our income prediction model. So I started with some pre-processing. This included one-hot encoding for the categorical features, scaling numerical features with standard scalar, and carefully cleaning the target variable income to fix any inconsistent formatting. These steps made sure that the dataset was standardized and ready for modeling. For model selection, we used two approaches. I started off with logistic regression, which served as a simple, interpretable baseline, while random forest was chosen to capture a more complex relationship in the data. Both models were trained on the pre-processed data. To illustrate the predictions, I created two hypothetical records. The first represented a lower income profile, a 30-year-old male working in sales with no capital gain or loss, working 40 hours per week. The second represented a higher income profile, a 50-year-old male, self-employed with a master's degree in executive managerial role, reporting a $10,000 capital gain and working 60 hours per week. Oh, let me just double check. Okay, perfect. After pre-processing these records identically to the training data, the random forest model predicted less than or equal to 50K for the lower profile and greater than 50K for the higher profile, which aligned with expectations. Now for part 4, in terms of evaluation, the random forest slightly outperformed logistic regression. On the test set, the random forest achieved an F1 score of 0.663 compared to 0.63 for the logistic regression. Cross-validation confirmed this trend, with random forest scoring 0.673 versus 0.659. Random forest showed stronger recall and overall F1 score, meaning it was better at identifying high-income individuals, while logistic regression had slightly higher precision. So finally, in the interpretation of results, I can conclude that the random forest captured the underlying patterns more effectively. Its prediction for the hypothetical records were consistent with its overall performance. Now, looking ahead, for further optimization, I would conduct some more hyperparameter tuning, and this could possibly improve the results even more. All right. Now let's walk through the process we used for car evaluation dataset. I began with some pre-processing. There was no missing values, but I did have to standardize the ordinal columns labeled 2 and 2.1. I did this by converting the entries like 5 more or more into some numeric values. and then casted them as integers. For unsupervised learning, I applied the one-hot encoding to the categorical features and scaled the numerical ones to ensure consistency across a data set. I then moved on to model selection, where I chose the k-means clustering, and I used the elbow method within clusters sum of squares to determine the optimal number of clusters. The curve clearly indicated that 4 clusters was most effective, so I trained the model with k equals 4. Now, in order to test the pipeline, I created 2 hypothetical records. Excuse me. After applying the same pre-processing steps, the train k-means model assigned the first record to cluster 1 and the second to cluster 2, demonstrating that the workflow could handle the new data consistently. For evaluation, I visualized the clusters using PCA. The plot showed reasonable separation between groups, and the elbow method confirmed that k equals 4 was a good choice. Finally, in the interpretation of results, I found that the numerical features 2 and 2.1 were the primary drivers of cluster differentiation. So while the categorical features showed consistent modes, the numerical attributes provided distinct profiles for new data points. Now here the linear regression model received a mean of R squared of 0.36554 with very low variability across folds, while the decision tree regression model had a mean of R squared of 0.0054 and much higher variability. This shows that the linear regression provided more stable and meaningful predictions. So from these findings, I was able to conclude that the linear regression was the preferred model for the dataset. The decision tree's performance was close to random, suggesting that it would need a lot of tuning to be successful. Now, before modeling, the dataset needed lots of pre-processing. The target variable was converted into string values, into I'm so sorry. So the target variable was converted from string values. I applied some one-hot encoding to the categorical features. I dropped the first category, and after pre-processing, the feature matrix had over 32 rows and 100 columns with a clean target vector. For model selection, I chose a linear regression for its simplicity and interpretability, and the decision tree for its ability to capture nonlinear relationships. Both were appropriate for the binary target and were treated as continuous for regression metrics. Finally, in model building and training, I use scikit-learn, where I imported the necessary libraries, defined the features and targets, split the data set, and then the evaluation was done using R2 scores and 10 crossfold validation, which confirmed linear regression's stronger performance. In conclusion, This project did take a lot of pre-processing across the different data sets to make sure that we had a clean, structured input. This was done by handling missing values, encoding categorical features, and scaling some numerical features. The models applied were logistic regressions, random forests, linear regressions, decision trees, and k-means clustering. Each data set was matched to the type and task, so whether it was classification, regression, or clustering. For the evaluation, logistic regression and random forest achieved strong classification accuracy, and F1 scores. The linear regression outperformed the decision tree in predictive stability, higher R2 squares. My apologies, R square, and lower variance. K-means clustering, we use K equals 4, showing meaningful segmentation, validated by PCA visualization and ELBA method. The interpretations of the results included the models providing actionable insights, so income prediction profiles, ABA ring count classification, animal shelter outcomes, and car evaluation clusters. So key takeaways: simple and interpretable models often provide stronger baselines, while more complex models captured nuanced patterns when tuned. So for next steps, things I'd take into consideration is that to improve the models, I could implement some hyperparameter optimization and some more specialized feature engineering. I would also maybe consider testing some additional algorithms, maybe some ensemble methods or gradient boosting. I could also do some more evaluations using some domain-specific metrics for deeper insights, especially with the first part of the project looking at a company. And so in conclusion, this project was a great example of applying real-world scenarios and walking through the whole data science workflow and process. And so thank you so much. For listening to my presentation. There's a lot of valuable insights collected during this whole process, and learned a lot during the whole process. Thank you.